presentations in between while we're giving speakers. Might be great to kind of stand up and stretch out in between our talks so we don't kind of fall asleep like I see in most of my lectures usually. Anton, who I just found out, went to, well, my PhD alma mater. He was there when I was there, so hopefully he doesn't have too many stories about me, but he is an environmental consultant at Scentroid. 5+ years of experience working and coordinating along various governmental, corporate, and academic institutions in the environmental field. He has his master's degree in environmental science from Wilfrid Laurier University, and his geographic area of focus is on North America and the Middle East. So join me in welcoming him for his presentation.
All right. Good afternoon. Welcome back, everyone. I know after lunch sometimes it is not that easy, so thank you. So this is Scentroid's second presentation today. I will be focusing on drone-based air quality monitoring. So I'll start off a brief introduction about Scentroid, who we are, what we do, a brief introduction about drone-based air quality monitoring, and then I'm going to get into some of the applications where this can be used, the methodology that's incorporated in it, and then I'm going to finish off with a brief case study example where, in our experience, we found the use of a drone to be absolutely invaluable. And thank you very much for the intro. A little bit about Scentroid. So we are a world leader in air sensory technology. We provide intelligent environmental solutions across a wide range of industries, and we manufacture a wide range of instruments related to air quality and odor monitoring. We also provide environmental services such as odor control, emission monitoring, air dispersion modeling, as well as provide recommendations and remediation recommendations, mainly for the purpose of environmental compliance. We have a global reach. So this image here is some of the countries that we're involved in. It's a little bit more now. We're in about 46 countries, but with the exception of Antarctica, we are present in all of the continents. An overview of some of the projects we've completed, I won't get into it, but they range from governmental agencies to environmental laboratories, academic institutions, and small, medium, and large-scale corporations. And the bulk of the presentation, drone-based air quality monitoring. So, as it stands right now, there are about 3 traditional main air quality monitoring technologies. And the first are air quality analyzers. Now, these are the most comprehensive systems. They are the most accurate systems, but they do have 2 major limitations. And the first is mobility, and that's because they are stationary air quality stations. So when they are generally set up, it is for an extended monitoring period. And the second is, another obvious one, is that they are very expensive. To give you an example, over the last 20 years in the Greater Toronto area, there's been about 3 dozen of these purchased and installed. And so the second approach, or the second technology, are mobile air quality analyzers, which are very similar to stationary air quality analyzers, except that they are mobile. Now that is an advantage, but not entirely, because they are still limited to roads and where vehicles can travel. And they share the same drawback of being very expensive. And the last one, this is a more modern approach, a more modern technology that's gaining traction, and that's the use of continuous monitoring stations, such as compact analyzers, compact air quality stations. And these are a little bit less accurate, but they cost a fraction of the amount that a standard stationary air quality analyzer would cost. So naturally then the question is, what else is out there? And one of these is a flying laboratory, which is essentially a miniaturized air quality station that is capable of measuring several chemical compounds. The sensors themselves are selected based on the specific industry, but some of the more common sensors that I've seen personally equipped on these flying laboratories are NOx, SO2, O3, VOCs, which is usually in the form of a PID sensor, CO and CO2, particulate matter, and some of the more common exotic sensors that I've seen are CH4 and HCl. So then, how does it work? And in a nutshell, it's actually very simple. The drone flies around and it collects data. Now with every data point, you're also collecting the concentration of the chemical compounds or pollutant, as well as background variables such as temperature, humidity, elevation, the latitude, longitude, and as well as the date and time. One of the unique features of drones is their data reliability. And what I mean by this is that there's three main data accessibility and, three main data accessibility centers and storage centers. And that's the onboard SD, the cloud server, and the ground station. And the onboard SD is the most reliable system, or the most reliable accessibility center. And that's because if there's ever any connection issue, for example, with GPRS, or internet, or with LoRa, if you don't have a direct line of sight with the unit, then your data will always still be stored somewhere, and that is on the SD card. The second one is a cloud-based server, and here you can log on, you have a username and a password, you log on to the URL, and from there you can change parameters, as well as view real-time readings, compare historical trends, fill a sample bag, so on and so forth. And the ground station is very similar to that, except it doesn't use an internet connection, but instead it uses a long-range LoRa connection, which is essentially a receiver right on the side of the laptop there, and then you have another receiver which goes into the drone, and as long as you have a direct line of sight, which we've tested in my experience to be about 1 to 2 kilometers, you're still able to transmit data. So what are some of the applications that drone-based air quality monitoring could be used in? And one of them is flare monitoring. And flare monitoring is an interesting one because flares are a significant source of pollutants, but most current methodology actually doesn't use direct measurement of the flare, but instead relies on estimations, such as knowing what the emission rate is, the gas exit velocity, and the gas exit temperature. Now, one of the advantages of a drone is that you can actually use direct sampling of the plume itself. A limitation is an obvious one with flares, and that's temperature, extreme heat. And there's two ways to get around this. One is there is a temperature sensor built in on the drone, and the drone itself has capabilities to create alarms. And in our experience, generally, whenever the drone reaches 60 degrees Celsius or more, then we have an alarm trigger, and from there we know we need to move back, pull back a little bit. And the second approach, and oftentimes these two approaches are coupled together, is we use a hanging line, such as a hanging PTFE line. So the drone is actually not flying directly above the flare, or pardon me, the drone is flying directly above the flare and not within the flare. And from there you have a hanging PTFE line, which is still sampling the ambient air within the plume itself. Another interesting application is for landfills. And landfills, once again, produce significant odors and pollutants. And traditional sampling of landfills is usually limited to a few fixed locations. And that's because, well, they have to be where you can easily access them, where you can travel to, such as roads. And with drones, the advantage in this case is the sampling plan itself. You are not limited to roads. So for example, you can have a sampling plan using a grid-based approach such as this, or you can make it a little bit more complex and involve additional sampling points, or if you really wanted to, you can make it completely different. And the point here is not that you can come up with really interesting and wacky sampling plans, but the point here is that you are in control of the sampling plan. You are not limited to fixed locations, you are not limited to roads, but you can sample the entire area. And from there, you can increase the area covered, increase the data obtained, and provide a greater overview of the facility itself using less resources. And another main point here is that it keeps workers safe. And really, this is because in a landfill, a lot of the times you'll have substances that are not safe for human contact or not safe for human inhalation. And with the drone, you can completely bypass that. Mining industry is another application. And particularly in this industry, we're looking at particulate matter in an open pit mine. And traditional sampling or monitoring of these mine pits requires an extensive sampling plan, and if it's done by vehicles, once again, it is only where it is accessible by vehicles. So you can see with that image, you'll be going around in circles, or you'll be using multiple operators to create a sampling plan. Now, with the drone, you can create, for example, a much simpler sampling plan with one operator. With that, you can increase the area covered, the data obtained, and once again, provide a greater overview of the facility using less resources. And another interesting application of it here is if you take a look, right where that star is, you notice that it's in the middle of a little pond, and that's a tailing pond. And with drones, once again, you can keep workers safe because no one has to go and sample that, and you can fly directly overhead and collect an ambient sample from there. And the last application, the last example I'll go over, is that drones also enable for the monitoring of large storage tank farms. With this, you can detect abnormal leaks or emissions. So for example, if you have an H2S or an SO2 or even a PID sensor, and you're flying over these large storage canisters or storage containers, if you notice a spike in the emissions or in the sensor readings while you're viewing the real-time data, then from there you can make an assumption that most likely there is some sort of leak here, there is some sort of abnormality. Once again, it is efficient, you save time and manpower, you only need one operator, one person. The sampling plan does not need to be split between multiple users, between multiple technicians or engineers. There is no, you take the north side, I take the south side. It's just, I'll take everything. And once again, it's safe. You avoid putting workers at risk because the operator is most likely sitting somewhere comfortable, or in a more practical scenario, is in the middle of the field, sampling within a line of sight. The methodology. And the first thing, and the most important thing, is the sampling plan. Now the sampling plan dictates everything. Where you're sampling, for how long, the height, the sensors that are installed. And the sampling plan is generally based on three main points, and we've added them. And the first is existing pollutant data. And with this, really what we mean is, if we are aware that there is a higher concentration of emissions from one portion of the facility, then obviously that needs to be taken into account within our sampling plan. The land use data. Is there a residential dwelling or a residential neighborhood directly adjacent to the site? If so, that needs to be taken into account. What is the predominant wind direction and wind speed? That needs to be taken into account. And the flight route. So, how is the drone, what route is the drone going to be taking? And from my experience, there's three main or traditional flight routes that I've seen. And the first one is a grid-based approach where, just like it sounds, basically fly around in a grid. And the second one is an international standard developed by a couple of German authors. It is the EN 1684-2. And this is used for drones for direct sampling of the plume. And then by far the most common and the most simple method is the stop-and-go method. And the stop-and-go method can be seen as an example in that bottom image, where essentially, just as it sounds, you fly, you get to your sampling location, you stop, you sample, and then you move on to the next location. And this one is really interesting because with this you can create your own sampling route, you can create your own sampling plan. And the last one, and this one may be a little bit less significant, but it's one that in my experience is almost never taken into account, and that's the takeoff in the landing zones. And the important part with this is that drones, typically, because of the payload is about anywhere from 2 to 4 kilograms usually, your drone itself will usually have a flight time of about 20 minutes. So you need to be able to take into account where you're taking off, and by the end of it, where you will be landing. So you've done the sampling. You create the sampling plan, you gather the samples. An optional step is to send them to a laboratory for analysis. And the reason for this is that the laboratory is, one, accredited, so you know what type of procedures are going into it. And it has no QA/QC method, so you know the results of the multi-point calibration curve, and so on. Additionally, for example, if you're sampling for VOCs on a drone, you usually have a PID sensor, which will give you just your total VOCs. But if you send it to a laboratory, you get a much more comprehensive list of the individual VOCs and their individual concentration. And then that data will be used to support the results from the drone itself. So you got the data, you got the sampling plan, you've analyzed it. The last step is to report on it. And the report will include the concentration of the compounds. It's going to attempt to correlate the compounds to the specific sources, identify areas of high concentration, and as well as compare the results to any pertinent guidelines or regulations. And from there, they'll know whether or not you are within environmental compliance. Two interesting applications that you can combine drones with. One of them is GIS. You can input the data into the GIS software for an enhanced visualization. You can view the data based on the pollutant time or concentration. And I'm going to move a little bit quicker here. The next one is thermal technologies, and this one is interesting because a lot of the times you'll have these large plumes where you can directly see with your eye that these need to be sampled. These are high emitters. And other times you'll have these basins or these storage tanks which to the naked eye look like they are perfectly normal. But with thermal imaging camera, you can actually see that there is a leak coming from them. And the same thing can be said with industrial dumping. So this is a body of water, and from there we can see that the surrounding water is a different temperature than the water here. And that could likely be as a result of industrial or civil dumping. And using a drone, using thermal imaging, you can actually identify and sample that. And the very last bit I have here is a case study that I'm going to finish off on. And that is a natural gas refinery that we did in Doha. So the issue here was that the municipality, it was on the outskirts of Doha, and they were receiving odor complaints. It appeared that the odor strained very considerably because some days there would be a large amount of odor complaints, and then other days there would be none. So Scentroid had an extended on-the-ground sampling campaign, which lasted for a total of about 2 years. But a few months in, Scentroid team noticed that the odor concentrations and the odor complaints seemed to peak during flare episodes from a nearby gas refinery facility, which was actually over 100 kilometers away. So Scentroid drove to the new site, to the new town, and from there, used the drone for sampling within the plume. And from sampling at different elevations and different distances from the plume, and we can see that this plume is several kilometers in length, we then took sample bags as well, took that data, sent it to a laboratory, sent it to 2 laboratories actually, one for olfactometric analysis and one for analytical analysis. And then we sent that data to a third party, which reverse modeled it, and we determined that the potential extent of the odor plume could register complaints up to 120 kilometers away, which was within where our